All right, folks. So we are at the kind of tail end of our unit here, and now that we've learned about gravitation and circular motion, it's time to put them all together. And the place where those two concepts meet is outer space. So we're talking about satellite motion today, orbital motion, basically um, artificial satellites that are traveling around the Earth right now. They travel around the Earth in pretty much a circular orbit. For planets, the closer a planet is to the sun, generally, the more circular its orbit is. So, like Mercury has a more circular orbit by far than like Neptune. Um, and so, for our purposes, we're going to treat every orbit as circular. We will update that later in the course, but for now, we're going to imagine that anything in space that's traveling around a planet or a star is traveling in a circular pattern. And so our first kind of question is, every satellite has its own speed. Now, planets don't travel at constant speed, but we're going to pretend that they do. Artificial satellites, for the most part, do travel at constant speed. And so we are going to probably focus a little bit more on that idea um, for now. So we have this like satellite, little m, traveling around a planet, big M. The distance between the centers of those objects is going to be r. The velocity of the object is v. That always points tangent to the circle that it's tracing. As far as like vectors that point inward, we have acceleration and net force both point inward. That's hard to read, but it says acceleration, comma, net force. So the understanding here is the thing that keeps a satellite in orbital motion is gravity. There's no stuff out in space that's going to push or pull on a satellite, especially like the further out of the atmosphere you get for planet Earth, the less air there is. And so at a certain point in time, there's like functionally no air. And so there's no air resistance. The speed of the satellite will like never deteriorate because there's nothing hitting it. So it's just gravity. Um, so as far as like this big question here, how does the orbital speed of a satellite, what does the orbital speed of a satellite depend on? We start with the understanding that this object is traveling in a circular path. So we start with circular motion and the centripetal net force. Now, the centripetal net force in space is purely due to gravity. Now, gravity is acting like is caused by every object in the universe, but for something like the moon or the International Space Station, the Earth is by far the closest thing to it and the most massive close thing to it. And so the net centripetal force is going to be the force of gravity due to the biggest object near it. And so this is going to be Newton's universal law of gravitation, law of universal gravitation. And the force of gravity that the planet is exerting on the satellite is the thing that causes that centripetal net force. M, the little m, is the mass of the satellite. And then I'm going to put in v squared over r for acceleration because we're looking at orbital speed. And so this is kind of our central equation. Now we're going to derive this expression for speed, have a v equals expression. And so there's a couple things that you can notice. One thing is I can divide both sides of this equation by little m, and it will go away. Meaning that the mass of the actual satellite is not relevant to its orbital speed. So that's one thing. The other thing I can do is I can multiply both sides of this equation by r. If I do that, r cancels here, and r squared just becomes r. And so our like central equation for orbital speed is if I solve this for v, right? This is like v squared equals g big M over r. I can solve that for v and get g big M over r. So this equation is like the central equation when we start to think about satellite motion. It deals with the speed essentially based on only, depends on the mass of the planet. And so, we're mostly going to focus on the planet Earth, but it could also be whatever star a planet is orbiting, and the distance between the centers of objects. Just remember that when we think about gravity, it's the distance between the centers of objects. We only consider things that are like perfect spheres. So it is literally the center of mass of the Earth to the center of mass of the satellite. Again, we'll talk about center of mass later, but there it is. And so this is it. And so what we're going to just talk about here is what happens if you need to like change the orbital distance of a satellite, like what do you need to do? So if we focus mostly on things that are around Earth, then this mass is constant. And so the R represents, or it incorporates the orbital height of a satellite, and that is only based on the speed. And so if we think about this satellite, very quickly using just this equation, if I wanted to take this satellite and bring it to a greater orbit, a greater height orbit, so take it to this R prime. The idea is this is now a greater value of R, it's a greater orbital distance. According to this equation, so a higher orbit means a greater value of R. Well, what that really means is in order to do that, it's kind of complicated more so than this, but the end result of having a higher orbit is a slower satellite, which might be counterintuitive. But from like an actual operating a spacecraft or a satellite point of view, if you're going to move a satellite to a higher orbit, you need to essentially do two things. Exert some force with like whatever like thrusters are available on the spacecraft to push it out of the circle. At the same time, or not at the same time, after you do that, you need to slow down the satellite to a smaller speed than it originally had. So this equation kind of governs what is necessary. The slower the satellite, or rather the higher the orbit, the slower the speed is required to make that happen. It's probably worth talking about another aspect of this equation, is that this represents the exact speed needed to keep this exact orbit. If and this kind of goes counter to what is being said here, but if the speed of a satellite increases for whatever reason, then that's going to kind of overcome gravity. If we go all the way back here, this greater speed, the speed is matching the force of gravity. The greater the speed, the further out of the circle that satellite's going to go. And it has a chance of escaping orbit. And so one thing that happens here is if you have a V that's greater than necessary, then the object is going to start to spiral outward and eventually completely escape orbit. If you have a speed that is too small, then the satellite would trail inward. It would spiral inward to the planet, and it would hit the planet's atmosphere and burn up. But in terms of like very careful changes, in order to get to a higher orbit, you would eventually need to have the satellite moving slower than it was originally. And so this expression represents kind of like the perfect speed needed to keep a certain orbit, and then this proportionality, the inverse proportionality, means a higher orbit requires a slower satellite. So we'll do more with that in class. The final thing I wanted to do on the video is Kepler's laws of planetary motion. That's something that we don't talk about a ton in this course. This question is basically asking you to derive Kepler's third law. And it has to do with how the period of a planet's motion depends on its distance from the planet. So as far as this goes, here's what we're going to do. The planet is still subjected to just the same situation that the satellite was subjected to. So we have the net centripetal force equals mass times acceleration. The force of gravity is the net centripetal force. And so we have all the same variables. So I'm just going to get this back to the same expression we had. We can cancel mass, we can cancel one of the r's. So g m over r equals v squared. And so the thing that we're going to do differently is understand that if it's moving in mostly circular motion, the period is equal to 2 pi r over t. And so we're just going to like mess up this equation. So I have g m over r equals 2 pi r over t squared. And so we're just going to like rearrange the heck out of this and solve it for t. So the first thing I can do is simplify the right side, or rather just take the square of the right side. I get 4 pi squared r squared over t squared. All right, so that looks like yikes. And so I'm going to just do some rearranging, and I'm going to try and do this in like all the steps that you would want to do. I'm going to take this entire equation and I'm going to multiply it by r over t squared. Okay, so the purpose of that, no, that's not what I'm going to do at all. That's not at all what I'm going to do. I'm going to multiply both sides of this equation by rt squared. And so the purpose of that is to basically get rid of the denominators. The end result that I would have is gmt squared equals 4 pi squared r cubed. And we're almost done. So I would then divide both sides by gm. I would get t squared equals 4 pi, oops, that's not right. 4 pi squared r cubed over gm. And I'm going to pause here. Basically, what you're looking at is Kepler's third law, kind of the way that he would write it. The square of the period would depend on the cube of the radius. And it also depends on the mass of the sun, essentially. To solve it for t, if I take the square root of everything over there, a bit of it simplifies, right? I basically take the square root of everything over here, and 4 pi squared becomes 2 pi again. I get r to the 3/2 power over the square root of g times m. So it's not technically part of this course, although I have seen a question or two on it on an exam. But this is, one of the bigger derivations in all of physics, I would say, is taking the understanding of gravity and circular motion and deriving what became Kepler's third law, describing the planetary orbit, the period of planetary orbit in terms of the distance from the sun. And these would be like average distances, and this equation works like surprisingly well to describe the average orbital distance of every planet. And so we'll work with problems for that in class.